invitation and for being here. Actually, David, we met when we played soccer together. So maybe we should all take this as a good reminder that once the pandemic is over, the ICFO-IMPRS thing, we should also have a soccer tournament. I think many would appreciate it, I guess. But good, let's get to physics. So I have to share my screen, I guess. Okay, so I hope it works. Can you see it? Okay, good, perfect, good. Yeah, so I want to talk in this talk about Meson formation, and that's what this ERC starting grant will also be largely about. Basically dynamical signatures of basically fancy effects in strongly correlated quantum matter. Before I really get started, I want to acknowledge my collaborators and the things I will present, the summary of many research projects we had, but the key players on the theory side, Annabelle and Eugene, then experimentally, lots of work, lots of projects with Markus Reiner's group at Harvard, Immanuel Bloch's group at MPQ, and Jeffrey here, there's one experiment in particular I will show, so he was the lead author there. And on the theory side also, I should mention Lode and Michi Knapp's group. Yes, so those were of course, some of the people, and there's always a big list of people contributing. So, I hope that this workshop here will also stimulate new ideas. All right, good. So I think this entire field that we're part of, really this quantum technology and using quantum simulators, quantum computers, even at some point, lots of it comes from quantum optics. And I think it's always worthwhile to remember what the actual fundamental paradigms of quantum optics were. And they used to be that we want to reveal and understand and control the individual particles, and in this case, that's mostly photons and atoms, on the most fundamental level. So basically, for many years, the goals have been to really understand every detail of the atoms and the electronic states in the atoms. Now, of course, the list has grown. We have qubits as well, and so on. But this is, historically where the field comes from. And of course, our generation is now part of a new, we're lucky because there's so much control that's been achieved. And we've heard several examples already over these individual atoms and photons nowadays, that in the labs, they can actually piece them back together. And of course, then you can study correlated many-body systems. And the first Bose-Einstein condensation was probably one of the examples that really, for example, set this field of cold atoms, but also quantum simulation really alight, you could say, right? We're still feeling the influence of these early experiments. But nowadays, okay, things get a little bit more complicated. In particular, quantum magnetism has been added to the list. Of course, it's a long list. We have heard about gauge fields before. But quantum magnetism, that's a field that also goes under this name of strongly correlated electrons. So basically, one can now use ultra-cold fermions, put them together, let them interact, get magnetic effects out, and see interesting physics. And Immanuel Bloch has told us quite a bit yesterday about what they can do these days in the lab. And my talk is supposed to basically add the theory perspective on those types of experiments, and I want to basically pick up where he left yesterday. So I can already tell you that these systems ultimately are believed to be, to model high temperature superconductors. I should also remind you maybe of the talk of Pablo Herrero. I think on Tuesday, he told us and said that when he entered this field of strongly correlated electrons, he realized how disputed things are in that field. And that's something you definitely feel in this field. The goal, of course, is to ultimately understand and reveal things like high temperature superconductivity. But okay, that's a challenging task. But I should say that the cold atoms really have added a lot because we can make definite checks now in clean models. So there's the hope, at least long term, that there will be much less dispute about the outcome. All right, good. But now let me get more specific. So I already told you that high temperature superconductors, that's what ultimately interests us. And so maybe some of you have seen this phase diagram before of high temperature superconductors. So that's what it looks like. It has two axes. The y-axis is temperature. And so, of course, it gets hotter in this direction. And a bit more interesting, I guess, is the x-axis. And that's what we call hole doping. So the idea is that at zero hole doping, that's what people call the parent compound, These systems are mod insulated, one atom per site or one electron per lattice site, and they form antiferromagnets. So think of electrons, the spin 1/2, and the type of spin pattern they prefer is up, down, and so on. So like a checkerboard lattice. And as soon as you take some of these spins out and create holes, then that's the x-axis. The number of holes you create, that tells you how much more complicated things get. Okay, there's optimal doping at some point. You get this, high temperature superconductors here. Ultimately, it's really the holes that carry this supercurrent. That's what's understood. But then there's lots of things that are not so much understood, like these exotic phases here, pseudo gap, the strange metal phase. There are these density wave or stripe phases, and there's at some point you get a Fermi liquid over here, many believe, but how these are all connected, that's really unclear. So I think, of course, there's a long story to this phase diagram, and lots of things have been found and understood also, but I think what's really lacking still is a unifying theme. And that's what many are searching for since years. And I think the cold atoms really have a chance to make a contribution. All right, so maybe before I get into it, I find it funny from time to time to check with these high temperature superconductors, how close are they actually to actual real world applications? And turns out it's not so far off. So here, this is some Russian research project where they're building a high TC motor into a research airplane. And so they claim it's 70% more efficient. So, obviously it's the research, but on the other hand, these are engineers really working with these things. So that I find pretty amazing. And given that we also, we don't really have a theory that describes these effects. All right, good. So what's the approach now? On the one hand, we have cold atom experiments, and they are, in this case, already able to simulate very complicated models, let's say in this group. And we would like to use their power to really find out the underlying mechanisms and the underlying physics. So in that sense, it's really, we at least the long-term goal is to use them as a resource. And I want to show you in this talk now that actually we have already achieved first steps in that direction. Okay, but I want to actually start this with a little story. It may seem totally unconnected at first, but you'll get the idea of how it connects in a bit. And so that's the story of how quarks were discovered. So I'm really talking about the quarks, that make up nuclei. So we know, that's what we learned, that atomic nuclei are made up of protons and neutrons, and each of them is composed by a bound state of 3 quarks carrying 1/3 and 2/3 electric charges. So this is a nice review article, and I'll just highlight some of the things. Okay, it's the review is old, so this the time changes, but it basically says, okay, there are these quarks, and the situation actually in the 1960s was that physicists started to understand that these protons and neutrons had a finite size. So they started to understand that they're extended objects. But the great majority of the physicists at the time considered these objects to be soft objects with a diffuse internal structure. So they really thought of it actually like one of these plum pudding models of the atoms, decades before. But so they knew there's something, but it sort of looked fluffy. And then a real or let's say the analogy I want to make here is that if you look at cuprates, that's these high temperature superconducting materials, the situation is quite similar, actually. So we know that the holes, those are ultimately the charge carriers. But if you look around, the great majority of people would actually also consider these holes, the charge carriers, as more or less soft objects, much like the neutrons back in the days. And so, without a clear, rich internal structure. And in the case of quarks, of course, what happens is that we now know that they're really point-like quarks. And the way this was historically found, so Gell-Mann basically proposed this based on some SU3 group structure. Let's not get into the details, but what's amazing is that at the time, the idea of fractional charges was so repulsive to physicists that even Gell-Mann in his original paper proposed, he said that a search for stable quarks of charge 1/3 and so on, with higher energy accelerators would really help us to reassure us of the non-existence of these quarks. So not even the inventor really believed in them. So I think that's a good lesson to learn. And of course, the idea is, what happened historically first is that they did high energy measurements. So this is some particular cross section that they measured as a function of the energy. You can see there's this quite broad, there's lots of signal here at high momenta, at high energies. And of course, this is the analog of the Rutherford experiment in nuclei. So basically, this lots of scattering at high energies told them that they are indeed point-like particles. So the key achievement experimentally at the time was that they were able to access high energies, and that corresponds to short timescales, and really resolve this internal structure. And this really, if we take this analogy over now, and that's sort of the goal of my talk, I want to argue that the charge carriers in strongly correlated cuprates, or let's say Hubbard models, like they can simulate them with cold atoms, they may have a similar structure. Namely, you may be able to find more, well, we would call them emergent constituents, that the charge carriers actually have some internal structure. And so then you can ask, what's the achievement we really need? And I think this is what quantum gas microscopes have achieved. So if you look at condensed matter physics, traditionally, the way they look at systems is looking at rather low energy, long wavelength properties. But cold atoms, of course, they can achieve and look at, for example, non-equilibrium dynamics and intermediate timescales. And that's really a new regime that we can look at. And it holds the promise, at least, to reveal more of the structure that ultimately is in these systems. And that's basically the goal for this talk. And I want to basically get back to this first slide now and say that, you know, we can actually, what we do is we want to apply the same paradigms of quantum optics again. And, you know, we study these many-body effects that are pieced together from cold atoms, but the way we look at them, what we're going to search for is, we're going to search for emergent constituents that basically show up on intermediate length scales. So what we will do is look at scales of a few lattice sites, not one. On the level of one lattice site, we know exactly what's happening, of course. And the goal is that if we understand on a few tens of lattice sites what's happening, then eventually field theory should also, well, we should be able to formulate field theories that really tell us fundamentally on long length scales what's happening. So this is basically the outline. And so really, you know, put in words, we're asking, is there something like quarks or partons, that's the more general name, in these cuprate or strongly correlated materials? And before I really get into the more details now, I want to say that this is not a really old idea. So sorry, it's an old idea. So it came up when high TC superconductors were discovered. So Laughton and co-workers were among the first to bring up the idea, but it kept coming up over the years again and again by several people. So, but I think what's really lacking, much like in high energy physics back in the days, is a clear proof. And that's really what we're after. All right, good. So let me be completely specific from now on about the model. I want to study. The models are always Fermi-Hubbard models. So they're going to look like this, square lattices in 1 or 2 dimensions. You have nearest neighbor hopping T, we call it, and there's an on-site interaction. If 2 fermions of opposite spins are on the same side, you pay 1 unit of U. All right, so this is the models we want to look at, and we want to even say we look at the large U limit. So U is typically 8 tunneling or higher, it could be 10 or 12 tunnelings. And in that limit, you can basically integrate out these double occupancies. So you can remove them from your theory and you end up with a TJ model. So that's an effective model that only describes holes here and spins, but the doublons you basically removed from the theory. And then it's what you find is basically a competition now between, well, the motion of these holes on the one hand side, that's this first term, with tunneling scale T, so that's the energy scale, and the second is a spin exchange interaction, so that's J, and typically the tunneling is quite a bit bigger than J, so a factor of 3 is typical, so tunneling is 3 times J, that's a typical number you would get in these systems, and this right-hand term, that's what favors this antiferromagnetism, the fact that spins want to be up, down, okay. So that's the model that's widely believed to essentially describe these Hubbard type models. All right, good. So now, well, you know, my claim was somehow that we can find something like partons, the analogs of quarks in such models. And I want to give you an idea where they can come from and how they can form structures. And to this end, I basically, we will follow this path throughout the talk here. And the first step I want to take is I want to remind you basically of the talk by Emanuel Bloch yesterday, where he showed us in 1 dimension how it's quite natural actually to get fractionalization, that the underlying interacting electrons or fermions or atoms in their case can actually, well, their quantum numbers can decay and you can get these partons. That means spinons and charge-ons. Okay, and this is just a reminder. We saw these slides yesterday, but that's the experiment they did in Emanuel Bloch's group. They basically had an antiferromagnetic spin chain in one dimension. They removed one of the atoms, created this hole. That means spin changes by 1/2. Charge, that's particle number in this case, changes by 1. And then this charge basically moves in one direction. This domain wall here, that's what carries the spin. And it keeps this memory, whether these are 2 red or 2 blue ones next to each other. So you can see that really the quantum number is moving away. That moves completely independently of this hole. And then there are different timescales associated with these two. So again, this is first, this is the key thing, right? That this domain wall here, that's the spinon, and that carries the spin quantum number. This hole is what we call holon or charge-on. It carries only charge, but it completely forgot about the spin that was originally annihilated here, right? That's why we say it's really a spinless particle. Okay, good. And now in between, I should also say that's important, there's a string. Because if you look at this, you can see that once you cross this domain wall, you go from a blue-red pattern to a red-blue pattern. And so this is actually something that generically happens when you introduce partons. You always introduce some sort of fields in between the partons. So whenever you fractionalize quantum number, there's a string in between, typically a gauge string that connects these new fractionalized particles. All right, so these are the players. Again, I remind you of this slide from yesterday. So this is what they measured in Munich, the spreading of the hole, and then the spreading of the spin as well. So at first it looks like 2 light cones, but if you look at the timescales, this is 4.7 here, this is 18. So this red one, the spin is much slower. And of course, this is the slide Emanuel Bloch showed yesterday, that when you extract the velocities, indeed, the spinon has a velocity that escapes with a super exchange J, which is much slower than this fast holon or charge-on. So I will use these two names interchangeably. And here the velocity is tunneling T. Okay, good. So this was basically a quick recap about one dimension, what's been done so far. But I also want to show you, well, actually, before I get to the next slide, maybe just one comment on how you can formally describe these systems now. So more formally, what would be useful to do is to introduce fermion or write the underlying fermion operators. So Cj sigma describes the actual fermions, and you can write them in this Parton language here. So you write them as Hj dagger, that's a creation operator of hole, times an Fj sigma. So these Fj sigmas, that's what then carries the spin quantum numbers. That's why they're called spinons. And the cool thing is that in these 1D systems, to a good approximation, you can write the Hamiltonian as a sum of the two, one holon Hamiltonian, one spinon Hamiltonian, and then the wave function, because of the separation of timescales, the fact that this tunneling here is so much faster than the super exchange, you can factorize the wave function and write it as a product state. And this will become useful again if we go to higher dimensions in a bit. Okay, good. So this is basically what the experiments have already seen so far, but I also want to basically spend one slide telling you, still in one dimension, but what we think they can also still do, or we think they should do, to get even more insights into the physics of these partons. And the idea is to do spectroscopic probes. So over the past, spectroscopy has been actually the strength of cold atom experiments. And then the quantum gas microscopes came that have full resolution and so on with all their power. And spectroscopy, well, it moved a little bit into the background, but still they have the ability to do spectroscopy. So it's still very promising. And so now specifically, I want to talk about IMPRS. So this, in solids, that's angle resolved photo emission. And the photo emission part, that's the thing I want to draw your attention to. So the idea is you started your system in some initial state psi 0, let's say the undoped spin chain. It could also be a doped one. And then what you do is you remove one of these fermions. And so here in this particular expression, we remove it at a certain momentum k with a fixed spin sigma. And then the idea is this quantum state here is time evolved with this full Hamiltonian, e to the minus iht. And so this is a dynamical probe. You basically dynamically probe this spin charge separation. So this wave function that was precisely analyzed in these experiments that Immanuel Bloch told you about yesterday. But now the way spectroscopy differs is that you basically time evolve this wave function for a certain amount of time and then project back onto the initial state. That's this left part here. And then you basically Fourier transform in time. So it turns out this is a very useful way of thinking about, well, these dynamical experiments, because if you analyze precisely this combination of things, you will find that all the eigenstates that you have in your Hamiltonian will correspond to delta function peaks at the corresponding eigenenergies. And then that's why you basically get back the full spectrum here as a function of frequency. And momentum is also conserved. So that's also a good quantum number. All right. Now, if you look at these spectral functions, the question, of course, is how can you really in practice measure them? Because these overlaps that I'm describing here, they don't seem quite simple to measure. That's true. There are ways, but you know, it's rather hard. But it turns out what's the simplest way to do it is to work in a linear response regime. So this was one proposal we had specifically for quantum gas microscopes. So the idea would be, imagine you have a ladder system now where you first realize your spin chain in one of the legs of the ladder. And then you modulate the tunneling into this empty leg next to our physical system. And then, of course, this creates a hole like this here. And that's precisely the initial state we want here. And then you just let the time evolve. And after a certain time, you basically detect how often does it happen that you generate another spin in this detection chain on the right. It turns out if you use Fermi's golden rule and so on, the rate with which you create these excitations you can show is given by, it's directly proportional to the spectral function up here. And that means you basically run this experiment and all you have to do is run it a bunch of times and count. And you can change the frequency with that you modulate. At each frequency you count, and then you get the full spectrum. So something similar has been done in Wasim Barker's group in Princeton already. But this is a very powerful tool to get insights into the full spectral structure of your eigenstates. Okay, now, of course, the next question you could ask is, well, in one dimension, what can we learn? You know, how is there anything we can learn beyond what we already knew from this spin charge separation idea that spinons and chargons simply spread away from one another? And the answer I want to argue is that there's quite a bit we can learn. So let's take a look how the spectrum would look like. And well, the useful thing is, ultimately the spectrum is a Fourier transform. And I told you before that because of the separation of timescales between the tunneling and the J, that the wave function, we can think of it as a product wave function of the spinon part and the chargon part. And as a result, in the Fourier transform, if you Fourier transform a product wave function, you get a convolution of Fourier transforms. That's absolutely true. So here you get a convolution of the free holon and the free spinon part. And the spectral function here, so this is a full exact diagnosing calculation at finite temperature, but you can indeed recognize this convolution form because what's happening is there's this black line here indicates one of these chargon branches. And then for each momentum of this chargon on the black line, you can see there's a full branch here. Oops, sorry for this. There's a full branch. You can see these parallel lines here of spinon states. And so this spectrum here, even at some finite temperature, clearly reflects this convolution nature of the state. Okay, so that means, we knew that the chargon has simple nearest neighbor hopping. The hole just hops to nearest neighbors. So what we see here is basically a part of a usual cosine dispersion. The overall prefactor is the tunneling. So this is not so surprising. But you can think about it, and you will easily find that the spinons are much more difficult to understand, right? That's these domain walls. But then if one looks closer, it turns out that these domain walls are actually that's more like a pictorial way of understanding the spinons. In reality, there's more interactions, and so you have to be more careful. But now, if you look at this convolution interpretation, you would say that, well, these branches here, they also look like cosines, right? So that's this dash dotted line down here. And again, I just repeat this dash dotted line everywhere. For example, here it would also move over. So it also looks like a cosine, but really it only looks like half a cosine. So it starts from over here and then here it stops. So you could imagine asking, are there states down here on the right? We don't see any states, but maybe there are some states because it turns out there's also spectral weights in here that play a role. And so it turns out there's a very simple interpretation of this type of spectrum. And that's, if you think about these spinons, these F particles I introduced above, as forming a Fermi sea. So think of these F up, that's the red ones, and the F downs, the blue ones here, is forming a Fermi sea in a simple nearest neighbor hopping model. They fill up these states. And what we do now in this up is you kick out one of these red spins, and you ask for which momenta do you get, well, where can you basically remove one of these red spins? And you can see you can only do that from -π½ to +π½ in this range. So that means if you translate these momenta here, this blue dotted line here along this spinon dispersion, that it precisely corresponds to these states here with spectral weight. And then it turns out here, you also have in principle states, but they're unoccupied. So that's basically down here. And these unoccupied states, if you remove another spin, there's nothing you can see because there's no spinon to begin with. Turns, you can check that these states actually exist. You can find states here with the correct spectral probes and so on. But this means if you look at the spectra, you can basically find that the spinons in these 1D settings behave like free fermions. And that's, of course, a much more detailed insight already now into the structure of these underlying spinon excitations. Okay, good. So that's what I want to talk, or I wanted to say about one dimension. That now we want to get to 2D. It turns out there's an interesting analogy here. But if you're interested to this pseudo-gaps business, if you're interested, ask me later. I'll skip it now. Maybe move to 2D. But this is a good point if there are any questions in between.
So we don't have questions right now, but yeah, remember everybody, if you have questions, you can drop them on the chat during the talk, and then we'll collect them at the end. So yeah, I don't see any question popping up right now, so
that's fine. Maybe
we can continue.
Good, perfect. So then I will continue. And now, of course, we want to go beyond one dimension. So I want to show you that these mesons or more interesting bound states of these partons can form if we go to higher dimensional settings. So first, to give you some intuition, I already told you in one dimension what these partons are, these domain walls and these charges. Now I want to show you, well, give you the intuition why they're so much more complicated in higher dimensions. And the idea is, if you look at 2 dimensions, for example, when you create one of these holes, so you remove a spin 1/2 excitation, then of course what you do is you create, you remove a spin 1/2, right? So you create this sort of bigger defect now in 2 dimensions. And then the tunneling is the largest energy scale. So the fastest processes correspond to this charge on moving out here, creates a string of unhappy spins. So these green links in this simple lattice here indicate the links that are unhappy now, right? So if you look at these spins here, you have 2 up spins next to each other. That costs energy because they want to have this antiferromagnetic alignment. And in this simple model, and that's not actually such a bad model, you can see that the spinon at one end and this charge on the other hand, they are first of all still connected by a string, and furthermore, the energy of the string somehow scales linearly with the length of the string, because the longer the string is, the more unhappy bonds you have. And this is, of course, the main motivation why, if you have partons in higher dimensions, they should be much more interesting and form new structures on some intermediate length scales, essentially bound states of, for example, two partons like here. Okay. And of course, this is where the analogy with quarks comes in, right? In the nucleus, you also have quarks, but you cannot remove one of the quarks. That's this confinement idea. So something similar may happen in these 2D systems. Okay, so maybe, yes. So I wanted to basically add a few words how we can go beyond one dimension. So in one dimension, there have been a few papers. Of course, this is just a selection of papers in 2D. You can see 2 dimension since it is connected to this high TC phase diagram. It's a lot more work. This is only cold atoms, of course, right? So I think in solid states, tens of thousands of papers published on this Hubbard model. So these are the 2 obvious options. You can, instead of 1D, you can simply do 2D. You can also tune your tunnel couplings step by step, basically, slowly increase one tunneling along the second direction to continuously go from 1D to 2D. Cold atoms can do that. It's a wonderful, and they have done it so also at some point. So it's a wonderful way to interpolate. But I also want to quickly mention one more possibility that we think is quite promising, actually, and that's what we call mixed dimensional. So let me take this little detour and tell you what these mixed dimensional systems are about and what I mean with this. So the idea is we want to have a system that is still two-dimensional for the spins, but it becomes one-dimensional for the charges. And the proposal is to take a 2D lattice, but switch on a very strong gradient, that's this gray here, let's say along the y direction. So the strong gradient means much stronger than the tunneling T in that direction. And, oops, sorry. And this means now that, of course, when the holes move along the x direction, they don't feel the gradient, right? They're always at the same potential energy. But if they start to move along the y direction, they have to tunnel up and jump up this hill. That they cannot do if this hill is much stronger than this tunneling. And so by adding this gradient, you basically restrain your charges to move only along x direction. But at the same time, if you look at the underlying super exchange interaction, so that's what gives rise to the antiferromagnetism, where they come from is that when one particle would hop over virtually, that costs you some energy typically, and then it goes back. And usually and the same is true here in x direction, you get a t²/u type of process. Yeah, you go there, you go back, and in the intermediate state, you pay an energy u. So the j is going to be t²/u. But if you do the same along the gradient, there are now two options. You can either go up the gradient and back, or down the gradient and back. And now the super exchange has two contributions from these two paths, and one is t²/u plus delta, the other is t²/u minus delta. And so you can see that you can actually even tune the super exchange in this way, especially this u minus delta becomes interesting. If you want, you can even change the sign of your interactions. But in particular, the super exchange mechanism still works perfectly, right? So the type of model you then get that's this mixed dimensional Hamiltonian that we get, is that you only have charge motion along the x direction, but super exchange along both directions with tunable strength. But in particular, you can use a case where both j's are the same. So this is a model that can be realized. We think it's particularly interesting to see stripe effects. This is just a sketch. We look all that now. It's a calculation, but for a single hole actually in the middle chain. And the way these stripes look is so this gray area, that's the actual density distribution curve of this hole in the middle chain. So you can see it has a clear maximum in the middle, and the background color, that's your SZ expectation value. And what you can see is that it's red, blue. Wait, let's just have to shift it. Yes, red, blue on the left, and if you go to the right, it's actually blue, red. So you have to match it to your lattice sites. But if you carefully look, you can see that there's actually in the middle there's a domain wall. So you go from AB type order to BA type order on the right. And that's a typical phenomenon that is associated with these stripes, that when you go across this whole rich region, the sign of your Néel order parameter switches sign. Now, this is the same thing that happened in one dimension. Emmanuel yesterday mentioned these SC correlators, the spin-hole-spin correlators. But the remarkable thing here is that we only have one single hole in the middle chain, and nevertheless we get this the sign change of the Néel order for all of the chains. Okay, and so the interpretation, if you put it into pictorially, let's say, the interpretation is that you basically get a Parton formation, and in fact this looks a lot, for a 3-leg ladder, this looks a lot like a baryon, right, where you have one charge-on in the middle chain and then a spin-on in each of the other chains, a domain wall. And so this is like a bound state of 3 partons. And of course, the similar interpretation then is a peta-quark in this 5-leg ladder, where we see the same effect, still with a single hole. Okay, but this is sorry for this. This was just a little detour, basically, to give you an idea how if you change the dimensionality of your system in funny ways, it basically allows you to explore phenomenology like these stripes that's very ubiquitous for high TC superconductors in these somewhat simpler settings. Okay, good. So now I promised you, more dynamical signatures of these mesons in the title. So let's get there. And now we want to do basically full 2D calculations. And so in 2 dimensions, what I've always been talking about now is really the single holes, right? The charge carriers in these high TC superconductors. And there's now 2 competing pictures you can come up with. I've been talking a lot about this Parton picture so far, where I claim that these charge carriers we can understand them as bound states of spinons and chargons. But actually, historically, what people developed, and that's broadly accepted, is another model, the Polaron picture of these holes. And the idea is basically that the holes, when they move through the antiferromagnet, the idea is that they dress up with spin wave excitations, basically with flipped spins. Okay. And I should emphasize these 2 pictures, they're not really strictly exclusive, right? It's more like, as I told you in the beginning, when nuclei were discovered, the left-hand side basically assigns more like a fluffy structure to these charge carriers, right? There's this hole and then there's this dressing cloud of some sort of magnetic excitations. On the right-hand side, we say, no, look, there are 2 very well-defined partons. There's very clear and rich internal structure, and that basically sets these 2 apart. But of course, it turns out if you properly write down the Hamiltonian for these polarons, and you properly treat all the interactions between your spin waves, you may still actually describe this rich internal structure. But it's somewhat hidden in your formalism. Whereas what I'm advertising in this Parton picture is really that there may be a much simpler way to understand the charge carriers in these strongly correlated materials. Okay, and let's say the key consequences that are intrinsic to this Parton picture is, of course, there's separation of timescales between the spinon and the chargon that allows us to do a product wave function ansatz like Born-Oppenheimer. I'll get to that in a second. We definitely predict and expect always internal row vibrational states, right? Any bound state of 2 objects can also have excited states that are vibrating or rotating or so. That's less obvious on the left. Okay, that's sort of the distinction between the 2. Okay, now we've been putting in theory quite a bit of effort into describing these Parton bound states and these mesons. And I just want to sketch to you why it's so much easier to solve these models than, let's say, these complicated Polaron models. And the essence is what I mentioned before, this Born-Oppenheimer ansatz. So remember, the tunneling timescale t is quite a bit bigger than the super exchange j. And that means that our wave function we can actually write as a product state. Actually, of 3 components we propose. One is the squeeze space. That's always say the spin background. That's what's happening to the spins in the undoped system. Then there's the string wave function, and that's basically describing this fast charge motion. That's fast, it goes with the tunneling t, and therefore it factorizes from this last part, the spinon part. And so the basic idea is that the spinon can be slower or, it's going to be slower and have quite different properties, but we can still factorize our wave function in this basis, and that's quite powerful. And now, okay, the way we approach it in theory is basically different levels of approximations. One is, we call this the frozen spin approximations. We completely freeze the spin background and only include these string type fluctuations. It turns out it's quite powerful. It can describe many features, not all, but it's quite simple actually to even more or less analytically derive results. Okay. Then the second level theory is to add spinon dynamics. So you basically also allow the spinons to move. So the spinons, they act like this heavy nuclei in an atom or so, right? And so if at first you pin them, you just solve the electron problem, but then you also allow them to move, and that's also what we do. And the third scheme, or a third level of theory, would be when you also allow any back action on the spin environment. So that's much more involved, and that's still ongoing research a lot. Okay, good. So I could go in more detail into how precisely we describe, these string fluctuations and so on. But I think in the interest of time, I'll maybe skip this a little bit so that these are some subtleties. The take-home message is we can write down some effective Hamiltonian that describes how these strings fluctuate, and we can solve it effectively. Okay, so that's the essence. Good, but then I really want to get here. So this is now a dynamics experiment where the goal is to reveal this Meson structure of these charge carriers. And first I'll show you some theory predictions we had earlier, but then later the results of a recent experiment in Harvard where they really started from this undoped antiferromagnet with a single hole pinned in the middle, and then they released the hole. And so this is really, in some sense, the analog of the experiment that Emmanuel Bloch showed you in one dimension. They also pinned a hole or shot out a hole and let it go. And now the question is, what's different in 2D, right? And so the idea is that initially this, we create both the spin-on and a charge-on, because there's a spin 1/2 and a charge excitation. And at very short times, only the tunneling plays a role. And then these two can separate. And as long as they don't see this super exchange, this antiferromagnetism, effectively, they're also still almost like deconfined, right? They don't see that they're interacting, right? They just spread. So at short times, you would expect a ballistic expansion of this charge on. The spin-on is heavy, it goes with J. But then eventually, at a time scale of the order of 1/J, and this charge-on starts to feel that there's the string tension, right? So it cannot expand any further because it costs lots of energy to make long strings. And so at this intermediate time scale, we believe that a bound state of these two should form. Possibly still with some internal excitations, maybe vibrating a little bit and so on. And then lastly, at long times, we should be able to see that this heavy spin-on should also start to move. And that's essentially the same movement that in one dimension that this domain wall showed, except that now this charge-on is actually strongly bound to this very slow domain wall, right? So that's the naive picture we expected. And then we performed a numerical DMRG simulation, time-dependent DMRG, and looked at the Manhattan distance from this initial site. Okay, so this is an extended 4-leg cylinder. In the middle, one single hole was created, and then the distance of this hole to this initial site is basically measured. And you can see that indeed it has some different timescales. There's a clear initial spreading here. It turns out the velocity is exactly the tunneling, so it's really this ballistic initial slope that we expected. And then at long times, you can also see it's a ballistic spreading. So it's a linear slope here. It goes further and further away, but with a completely different velocity. It turns out this velocity is given by J. So that's exactly this slow spin-on dynamics that we expected. And the cool thing for us is that the agreement with this spin-on charge-on model is really almost perfect. So you can see it, that's this shaded area in the back. There's some intermediate time scales, a little bit difficult. There's some offset. But given that this is almost semi-analytic theory, the agreement is really remarkable. And it shows this key feature here as well. Okay, but this brings us to the question, can we, nail down this picture even further and see this internal structure of these objects? And to this end, what's very useful is to clarify in our head that there's lots of charge fluctuations. And so the way, of course, we would think of the wave function of these holes is as a superposition with some weights I didn't show here of all types of different string configurations. And typically, quantum mechanically, what we do is we take a wave function and we calculate the average, right, to get correlation functions, for example. But as you can imagine, if you have lots of different strings, the fact that you have so many possible configurations in the averaging very quickly leads to just a blob, right? Basically liquid-like correlations. So once you average over all strings, you can't tell anymore that there's actually always a string in each snapshot. And of course, the way out is to to look at individual snapshots and not average over them, but really look at them individually. And of course, quantum gas microscopes can do this, right? That's a great advantage, especially this full spin and charge resolution that some groups have achieved now. That really enables you to look for these strings in an individual picture. Okay, so this is what we did in DMRG, and so here's the procedure. So the idea is we get a snapshot like this on the left. There's a hole somewhere, a bunch of up and downs, and in general, this is not a perfect checkerboard pattern. To simplify our life, we want to compare it to this perfect checkerboard shown on the right. So what we do is we take the difference of these two images, and then you can see that some sides deviate from what we would expect in this perfect checkerboard. And what we now simply look for is these deviations in the vicinity of the hole. So in this case here, we would identify a string of length, in this case 2. And so what you can do now is you can, in the DMRG simulations, you can look at these string patterns and just simply count how often does which string length appear. And then what we showed here is basically the average string length with some background subtraction. But basically, we're looking at how much does the string length increase as we release the hole. And you can see that's the screen line here in the DMRG. So initially, it shows the same spread that we also see here. It also sees this bending off when the overall distance of the hole bends over. But of course, you know, the picture I sketched before was that at some point this bound state should form. So now this bound state should move as a whole. And that means our expectation would be that after this time roughly, the strings should not get any longer, right? Because the whole object moves as a whole. And indeed, that's what we find. And in fact, the strings, if anything, they get somewhat shorter. And this makes sense if you think that that the string is a bit long at first, it vibrates a little bit, and then that these internal vibrations will be damped. You may emit some other collective modes. So this makes sense, right? And indeed, if you compare this to our string theory, that's the green prediction, then you can see that initially it works perfectly. Here it's okay, and then here there's some clear offset, but at least qualitatively, the fact that it settles off, that's correctly captured. Okay, good. So of course, to describe this, you only need a first level theory. To describe the spreading here, you also need the spin-on motion. That's our interpretation. So you need the second level theory. These are all things we checked, and things work out. So we're happy about that. Okay, now I promised you to talk about the Harvard experiment. So they did exactly what I described now. So you can see this is an image. They have this hole created initially here. That here is some imaging defect. Don't worry about this. So this is the experimental region that they isolated. And then they have this hole here. They release it and let it go. So it turns out for better statistics, if they look at short times, they have 4 holes at the same time. But don't worry. That's the detail. Okay, and here what they're showing is this root mean square distance. It's almost the same as this Manhattan distance to this initial site that I showed you before, and as a function of time. And let's look at the data points. So far, that's the u over t equals 8. That's these blue ones. You can also see this initial ballistic spreading here, and then this bending over that we predicted. And then, well, you can see that's very challenging experimentally to get lots of data for a single hole when the hole's already somewhere here in the outer rim. So that's hard. That's why the noise is still a bit high. So these are impressive experiments, but one would hope to get a bit longer, of course. What's also remarkable is if you compare this to this green line here. So that's u over t equals 17. It turns out that's a much smaller super exchange J. And indeed, you can see that the slope that these data points show, it seems to be lower. There's lots of noise, you can argue, but at least the trend seems to be correct. At the same time, this red line here, that's a first level theory, just the strings fluctuating and no string tension. That's, they're at finite temperature. So we expect there should be interactions, but you can see indeed that if you don't include the string tension, it seems like it's clearly too high at these long times. So there should be some interactions between these partons. And the fact that these data points are consistently below this really suggests that these interactions play a role. Okay, good. They also looked at how the spin background basically is recovered. I'll maybe skip this detail. The theories also work well. That's basically a take-home message. And in the last 2 minutes or so, maybe just advertise one more thing. So the logic is the same as in 1D, right? So one of the next possible steps would be to do a spectroscopy as well, to learn more about the internal structure of these mesons. So that's what we've been working on a lot in theory. Basically the essence is, again, we have a product wave function. So we expect a convolution of a spin-on and a string part to describe these spectra. And the key message maybe is that the string part, the string is now strongly, or the chargon is strongly interacting with the spinor. And that means for the string part, we expect a discrete level structure, right, with discrete level spacings. And this is completely different from one dimension. In one dimension, the chargon or the string is completely free, but now we should get discrete lines. And this is indeed what's found. So this is an IMPRS spectrum, again calculated with DMRG. You can see this lowest peak here. That's the ground state, and there's a parallel. That's like the first vibrational mode where the string is vibrating a bit. And now comes, this is really the last minute I will talk, but the idea is that if you have two partons, there's two options. One is that these strings fluctuate like this. They basically, their length is oscillating. But another appealing option is that if you have these two partons, they can also rotate around each other. And in general, you would expect to see rotation in these types of spectra, right? But if you look at this now, there's at best one vibrational mode here, and so these are, we think, are artifacts of this numerics. So there's no clear peaks below here, and so somehow we're missing these rotational peaks. And it turns out the reason this is so is simply because the type of spectra calculated here, they do not include angular momentum between these two partons yet. So you create them at the same side on top of each other, and that means there's no rotation that we induce. But what you can do is actually you can, and that we recently proposed, a rotational extension where you basically put extra angular momentum into the system. Again, if you want more details, just let me know. I'll tell you later. And then what we find is this here. Basically, this is an energy cut on the ground state of the normal IMPRS spectrum. But if we include this angular momentum here, that's the upper two curves, you can see that there's a new peak showing up, a very pronounced peak here at energies to the left of this ground state peak that corresponds to higher excitation energies. But the fact that it's a very pronounced peak here, much more pronounced actually in this 2S, this first vibrational peak that I showed you before in the full cut, this really shows that there's this internal rotational structure of these mesons. And that's basically the analog of similar elementary particle peaks that people found in high energy physics, where you don't only find mesons, but you also find rotational mesons, and these are the peaks that correspond to those. Okay, good. So I really hope I could give you an idea how we try to find new paradigms in strongly correlated electrons, based and largely motivated and supported by quantum simulators, and also this new perspective that they allow. And I'll just close with this slide maybe. Yeah, so that's sort of the dream I'm pursuing, to which extent these mesons can ultimately also form collective states of matter, and get us new insights into this phase diagram. That's the long-term goal. Yeah, okay, so thanks a lot for your attention, and I'm happy to discuss and ask, and take questions, of course.
Okay, thanks a lot.